Hello students. In the previous class we discussed about this point. You just see what we have discussed in the previous topic. So previous topic we have discussed about the relation, this one, PV is equal to 1/3 mn URMS square. This is where we stopped. In case if you have not watched, just go to the playlist and you will get the derivation, which is a very useful derivation. Now what we are going to learn today. Today's topic is a relation between, we are going to derive relation between kinetic energy and absolute temperature. So absolute temperature means temperature in Kelvin system, right? So today's topic is this, so which is actually based on the previous topic. Previous video was becoming lengthy, that's why I'm making it another video. Actually in classroom we used to explain this along with that previous topic, right? Now, so here what we are going to do is, let us take container, and here there are large number of molecules and have different kinetic energy, right? So let me say there is a bunch of molecule whose energy is same, because it's not necessary that each one will have a different. There might be some n1 number of molecules whose kinetic energy is, let us say, ke1. There may be another bunch of molecules, let us say the number of molecules is n2, and the kinetic energy, let us say it is ke2. So, and another bunch of molecules, there may be another bunch of molecules, a total number of molecules is n3 and kinetic energy is ke3, right? This is what we are thinking, because as per kinetic theory of gases, what it says is all molecules have different kinetic energy. So it is not necessary that all will have different. There may be some bunch of molecules where their kinetic energy is same. There is another bunch of molecule whose kinetic energy is same, like that. Now I want to find the total kinetic energy. So the total kinetic energy is equal to sum of the individual kinetic energies, which means ke1 plus ke2 plus ke3 and so on, right? Now what is the formula of kinetic energy? Is equal to half mv square, half into m into v square, but this is of n1 number of molecules. That's why I have to put n1 into v1 square, because there are n1 number of molecules whose energy is ke1. So m into n1 v square plus second kinetic energy. Here there are n2 number of molecules, so you can say n2 into its kinetic energy is half. Again mass is same. Again I am telling you, as per kinetic theory of gases, what it says, all gas molecules have same mass, so this is the postulate of kinetic theory of gases. So mass will remain constant, so but velocity it changes, so you can say v2 square. Got my point? And for third case, there are n3 number of molecules, and their kinetic energy, you can say half m into v3 square, and it goes on. Got it? Now what is common in this one? That's a half m is common. So half m, if you take it common, what will be there? n1 v1 square plus n2 v2 square plus n3 v3 square plus so on. Correct? Now what I am doing simple modification to this, that is half m, let us divide with the total number of molecule and multiply with total number of molecule. So you can say n1 v1 square plus n2 v2 square plus n3 v3 square plus so on. This you are dividing with the total number of molecules, which is n1 plus n2 plus n3, which is, let us say, n. and multiplying with total number of molecules. Yes, we can do. Now what is the use of this? Here this is the square of RMS velocity. That is what we have studied over there in the previous topic. I'll show you that previous one also. This one, you see, this is the what? RMS velocity, and RMS velocity square is that, right? N1 V1 square plus N2 V2 square plus N3 V3 square upon N1 plus N2 plus N3. So this is the square of RMS velocity. So what can I write? Half m into, this is the RMS velocity, you can say u RMS velocity square into n, right? Where u RMS is equal to, what is the formula for u RMS? N1 V1 square plus N2 V2 square plus so on, divided by total number of molecules, and it is square root. That is the formula of RMS. Now if you do square on both sides, so you will get that. So this is a since, you can say, since that point. Now so finally what we have got, kinetic energy Ke is equal to 1 by 2 into m into n into u RMS square. This is what we know. This is equation number 1. As per kinetic theory of gas equation, as per kinetic theory of gases, the kinetic gas equation is, what is that? PV is equal to 1 by 3 m n u RMS square. That is what we derived in the previous video. In case if you have not watched this, you just go through that one, so you will get more clarity. What I will do is, now I am dividing 1 upon 2. So what we will get? 1 upon 2 kinetic energy upon PV is equal to 1 by 2 m n u RMS square divided by 1 by 3 m n u RMS square. It get cancelled, so which is equal to 3 by 2. Now almost we are at the end. Now Ke, kinetic energy, is equal to, what can you write? 3 by 2 PV. But what we know, as per ideal gas equation, PV is equal to nRT, where n is number of moles. If n is equal to 1 mole, what will come? So PV is equal to RT. Can we say like this? PV is equal to RT. Now this value I am going to substitute over here. So which means kinetic energy Ke is equal to 3 by 2 RT. That is the final expression. So here the kinetic energy of any gas depends on absolute temperature. Apart from that, kinetic energy will not depend on anything. So I will explain this point. Yeah. So what we got here, Ke is equal to 3 by 2 RT. So here kinetic energy of any gas, because here R is a constant, so I can say depends only on absolute temperature. Absolute temperature means temperature in Kelvin system, but not on nature of gas. Means whether you take any gas like hydrogen, oxygen or helium, all gases will have same kinetic energy. Suppose example, you take at 300 Kelvin. At 300 Kelvin, the kinetic energy of hydrogen will equals to chlorine, will equals to nitrogen, will equals to sulfur dioxide or methane, etc. Any gas, if you say temperature, if it is same, then kinetic energy will be same. Kinetic energy depends only on one factor, that is absolute temperature. So it is not depending on mass. That is the final conclusion which is being asked in many MCQs. Now So here let me write the value of kinetic energy 3 by 2 RT, where R is equal to 8.314 joule per Kelvin per mole. But suppose if this is per mole, if I want to write for 1 mole, what will come? This is for 1 mole of compounds. But if I want for only 1 molecule, then what can I write? If I want only for 1 molecule, so kinetic energy will become 3 by 2 R divided by Avogadro number, correct? Because this is this is the value for 1 mole, yani 6.022 into 10 power 23 molecules. This is for these many molecules. But if I want for 1 molecule, what can I do? I have to divide with Avogadro number into T. Now kinetic energy is equal to 3 by 2 into it is 8.314 divided by what is Avogadro number value? 6.022 into 10 power 23 into T. So KE is equal to 3 by 2 into, if you can divide it, you will get approximately 1.38 into 10 power minus 23 into T. So that is kinetic energy is equal to 3 by 2 into, people call small k, into T. This small k is called as Boltzmann constant. It is called as Boltzmann constant. What is its value? Its value is 1.38 into 10 power minus 23. It is a joule per molecule. Joule per molecule. It is a very simple one. It is like as R value, but R value is per 1 mole. 1 mole means for these many molecules. But if I want only for 1 molecule, what should I do? I have to divide with Avogadro number. So Avogadro number is this. I have divided and I got it. This is the Boltzmann constant. So this is the formula for 1 molecule, generally which we used to do this in physics. But this is the formula for 1 mole of molecule. Generally in chemistry we do this one. This is for 1 mole of molecules and this is for 1 molecule. So I hope you understood this one. So this is the relation between kinetic energy and absolute temperature, right? Understood? So meanwhile you can pause the video, and if you want, if you like my videos, you can make the notes also, no problem. Now, so we have derived the relation between absolute temperature and kinetic energy. Now we are going to learn the another topic that is Maxwell-Boltzmann probability curve. Maxwell-Boltzmann probability curve. So let us see what is the main aim of this topic. This topic mainly discuss about velocity of molecules. The main aim of the topic is velocity of gas molecules. What kinetic theory of gases studied? So as per kinetic theory of gases, different molecules of gas or different gas molecules have different velocity, or I can say they travel with different velocity. So it is not possible to find the velocity of individual molecule. You cannot get a velocity of one molecule. But what this Maxwell and Boltzmann said, so they have drawn the graph. They have taken that the number of molecules or fraction of molecules. I'll explain this very detailed. You see, fraction of molecules. Here if you take a container, this is a container, right? So there will be large number of molecules, let us say infinite number or 1 mole of molecule. In this 1 mole of molecules, yes, all molecules have different velocity, but there will be some number of molecules with less velocity. That is what the Maxwell and Boltzmann said. The number of molecules with less velocity, very less velocity, would be very less. Okay, you must be getting little confusion. I will explain also. As well, the Maxwell and Boltzmann said the number of molecules with high velocity, the number of molecules with high velocity will also be less, but the number of molecules with middle velocity, or the average velocity, the number of molecule with middle velocity or average velocity is more, right? So you got little confusion. I will tell you with example. Suppose if you take 1,000 molecules, if you take 1,000 molecules, out of these 1,000 molecules, the number of molecules with velocity, let us say 100 kilometer per hour or 100 kilometer per second, this is a very high velocity. It will be very less number of molecules. Out of 1,000, let us say there are only 50 molecules with a high velocity. This velocity is very high velocity, very high velocity. Similarly, the number of molecules with velocity 1 kilometer per second, this is a very low velocity, so those number will also be less. Let us say it's not necessary to be 50, maybe 60 or 70, but the number of molecules with velocity, let us say 1 to 100 kilometer in between velocity will be, there are 1,000 molecules. Out of that 50 will be this one and 60 will be this one, so remaining is around 890 molecules will have this middle velocity. Got my point? No, samajh mein aaya? So if you understood it, then it's absolutely good. If you don't understand, I'll give you another example. Example number 2. So if you don't understand this, if you take a class of 100 students, class of 100 students, let us take. Now tell me the number of students who will secure less than 35 marks out of 100 marks exam. How many students will be there with less than 35 marks? Very less number of students, let us say 8 students. At the same time, the number of students with above 90 marks, people will also be less. Let us say 5 students. But the number of students with who have got 35 to 90 marks, how many students will be there? Totally 100 minus 13, which means 87 students, which means the number of students with very less marks, this is a very less marks, will be less. The number of students with very high marks, the number of students who have got very high marks will also be less. But the number of students who have got middle marks, that number is high. Got my point? Similarly, if you take many examples, I'll give you another example. If you take Indian population, the people with very less amount, very less amount means less than 1,000 rupees per month, there will be very less people, we call BPL, below poverty line. At the same time, number of millionaires means who are earning more than 100 crores per month, they will also be less. But the number of people with middle range salary or middle range income is very more. Got this one? So that is what they said. Yes, coming back to the point here. So out of these molecule, what Maxwell and Boltzmann said, this is the assumption. They said the number of molecule with less velocity will be less number of molecule. There will be less number of molecules with very high velocity also, but there will be very high number of molecule with middle velocity. Got it? Now examples, I have given 3 examples. Now based on this fact, I am going to draw graph. So based on those above facts, I am going to draw graphs, 2 graphs actually. First one graph let us study. The one graph is on x-axis I'm taking a speed, not velocity, because now I'm talking about scalar quantity, so it is a speed. And on y-axis, let us say the number of molecules. On y-axis, let us say the number of molecules. This is very less number of molecules. Number is, it is increasing, it is more increasing, it is further increasing. This is the speed. So now the number of molecule with less speed will be less. The number of molecule with middle speed will be very high, but the number of molecule with very high speed is less. Got my point? This is the number of molecule with low speed is less. The number of molecules, this is the number of molecule with middle speed, this is high, and the number of molecule with very high speed, this is a very high speed range, that number is less. Now if you join these points, so you will get a graph of bell shaped. So this is of a bell shaped graph. Got it? So now this is not a symmetrical graph, keep it in mind. Here, what is this point? You tell me what is this point. If you understand this point, then you will understand the whole concept. Yes, you tell me what is this speed. This speed is that speed which is possessed by maximum number of molecules. Am I right? This is this speed value. Let us say this is the x speed. This is the x speed. What is that speed? That x is that speed which is being possessed by maximum number of molecules, and that speed is called, that x speed is called as most probable speed. Most probable speed or velocity. Some people call velocity and some people call speed. Got. This is not the average speed. It will be average if the graph is symmetrical. But here the graph is not symmetrical. That's why this is not the average speed. This is the speed which is possessed by maximum number of molecules. So I can say it is a most probable speed. And below to that one, next adjacent to that, yes, if you can draw another point, yes, that is going to be y point, and that y point is called as average speed. That will be the average speed. And the another one next to that, one more line you will get, that is, let us say z, that is z, and that is called RMS velocity. You know RMS speed. RMS means root mean square speed. So this is the 3 points in the graph. This is drawn at constant temperature. At constant temperature T, let us say 300 Kelvin or any other temperature. Got it? This point. Now this is the first point is the most probable speed. Second point is average speed, and third one is RMS speed. The gap is little bit wider. Here the gap is more and here the gap is less. Why? That we will see also now. So experimentally it is proved, some derivations are there, so which is not necessary to you. So in the 10th, 11th or even college level also it is not needed. So directly I am going to those values. The most probable speed, which is indicated by the symbol C star. It is not necessary to be C star, but I am giving symbol. In many books it is used. Under root 2RT by capital M. Yes, R is a universal gas constant, T is absolute temperature, and capital M is molar mass. Got it? Now, we know that we have studied about relation between pressure and density. So pressure is equal to dRT over M. Right. From that, what can you write? P by M. We can write P by M is equal to, sorry, P by D. P by D is equal to RT over capital M. Can we say like this? RT over capital M. So that I can put here. So I can write under root 2 into pressure of the gas over density of the gas. That is the most probable speed formula. Right. Now next one, it is average speed formula. Average speed symbol is C bar. Generally people use under root 8 RT over pi m. 8 RT over pi m, which you can rewrite as instead of RT by m, what can I write? P by D. So 8p by d. Right. Now last one, it is RMS velocity or RMS speed. Simple symbol is C. You people know the formula. Do you know what is RMS speed formula? It is 3 RT over capital M, and which is given as under root 3p by d. This is the relation between most probable speed, average speed, and RMS speed. Now relation among these, relation between these three speeds. So C star is to C bar is to C is equal to what will come? Under root 2 RT by M is to under root 8 RT by pi M, then under root 3 RT by M. So in every case RT by M get cancelled. So what is left? Root 2 is to root 8 by pi is to root 3. So we can divide the whole equation with root 2. You can divide. So you will get root 2 by root 2. Then root 8 by pi divided by root 2. And root 3 by root 2. Which is equal to 1 is to, if you can do the simplification, you will get 1.128 and 1.224. Here you can see the gap. It is 1 is to 1.128. It is 1.224. The gap is little bit more. That's why I said you can keep little bit more gap here, because the gap is little bit more and here the gap is little bit less here. So this is the relation. Now which velocity is more, which velocity is less? Most probable velocity value is less, then average velocity, then RMS velocity. Now this people will remember like this. You have, if you want a technique to remember this, technique is RAM, or you can say RAM or RAM. So RAM, R is greater than A is greater than M. So R means RMS velocity, A is average velocity, and M is most probable velocity. So technique is RAM. So RMS velocity is more than average velocity, then most probable velocity. Got it? So it's a very simple one. This graph is main thing. In this graph, what I am telling is, this is the number of molecule with less speed. This is the speed, less speed I can say. The number of molecule with less speed will be less. At the same time, this is the high speed. The number of molecule with high speed will also be less, but the number of molecule with middle speed will be more. Like in the Indian population, below poverty line, BPL people are very less and millionaires are less, but middle class people are more. This is the same way. So these are the different types of speeds. Got it? I hope you understood this one. It's a very easy topic. Now continuation. Now you understood the different types of speeds. Now I'm going to explain the effect of temperature. Effect of temperature on probability curve. So I said there are two graphs. This is the second graph. Probability curve. Effect of temperature on probability curve. What we have understood, the most, whether you take most probable velocity or average velocity or RMS velocity, you take any velocities, in the formula it is very clear, they all are directly proportional to temperature, correct? So they all are proportional to temperature. Means as temperature increases, these all velocities will increase. So we have drawn the graph. Let us recall the graph. This is the speed on x-axis and the number of molecules or fraction of molecules on y-axis. We have drawn the graph like this. Remember, the graph is not symmetrical. It is not 50% distributable. This is the graph of, let us say, hydrogen gas at 300 Kelvin temperature. Now the question is, suppose if temperature is a 400 Kelvin. Suppose if temperature is 400 Kelvin, what would be the graph? That is the question. So this is the most probable speed, correct? So this is the most probable speed. You can say C star. Now what we have studied, as the temperature increases, most probable speed also increases. That is what we studied. So this means this point, most probable speed will increase. So the graph will broaden now. Now the graph will broadens. So the number of molecules, this is what number of molecule having the most probable speed, that number will decrease, and this is now the most probable speed. This is the graph hydrogen at 400 Kelvin. Got it? So this is the C star. Now this most probable speed, that is increased. So the graph, what I mean to say is one point, that is, as temperature increases, all kind of speeds, whether you talk about most probable or average or RMS, all kind of speeds increases proportionately, right? Second point, the graph is broadening. But the total area under the graph, total area, if you can find, it will remain same. So it means on increasing the temperature, so what is happening? Graph broadens, but the total area under curve, the total area will indicate ultimately the number of molecules, which is not going to change. On heating, temperature increases, so number of molecule does not change. The area under this curve indicate what? Number of molecules, which does not changes. So but the total area under curve remains constant. This is point number 2. So these 2 points we should keep in mind. Now the question is, so if you still increase temperature, then the graph will still broaden. Suppose 500 Kelvin, if you say 500 Kelvin, the graph will be like this. This is the same gas at 500 Kelvin. So as the temperature increases, the height of the graph decreases. You see, height of the graph is decreasing, and the most probable speed is increasing. Now you may ask me, sir, you have taken hydrogen gas. What about if you take different gases? So let me give you the graph. I am giving you 2 graphs at constant temperature. This is the graph number 1, and this is graph number 2. This is X graph at 300 Kelvin, and this is Y at 300 Kelvin. So what can be the X gas? X is Cl2 and Y is N2, or X is equal to N2 or Y is equal to Cl2. So I am talking only 2 options, that's why 2 gases. So the question 2019 JEE, the question is asked like this only. So which is that gas? That I have to predict. Got it? So here I can apply the very simple point. This is the most probable speed of X gas. this is the most probable speed of Y gas. Let us say this is the X, this is Y. Here X is less than Y. Is it clear? So what we have studied is most probable speed formula is under root 2 RT by M. So here most probable speed is inversely proportional to root M, which means if the molar mass is more, most probable velocity will be less. Got it? If molar mass is more, most probable velocity will be less. Now you take chlorine. What is its molar mass? 71 gram per mole. So and N2, what is its molar mass? It's a 28 gram per mole. So it is a very clear molar mass. Which one has more molar mass? Molar mass of Cl2 is more than N2. So if molar mass is more, then most probable velocity of Cl2 will be less than N2. So it means the X is about Cl2 and the Y is about N2. Got it? So this is all about questions or the type of effect of temperature on probability curve. 2 points. As temperature increases, all kind of speeds increases. And on increasing temperature, graph broadens, but the total area under the curve remains constant. And if you have two different gases, then most probable velocity is inversely proportional to root M. So now actually I want to give some practice questions, but this video is already long and few people get bored after seeing this video. That's why I will explain the numericals based on that in the next video. Right? Thank you guys.
Subscribe now and press the bell icon. Never miss an update. Subscribe now and press the bell icon.